Okay, let's get to getting. So we need to get through this material to start to present or discuss the lab for Monday, because you're going to be doing Newton-Raphson solving multi-variable equations. And we're going to see how we're going to apply that here to, this is going to be, we'll do it to a two equation, two unknown, but you can have a number of equations as long as you have the same number of unknowns, primarily because when we use it with multiple equations, we have to set everything up in a matrices. And when you invert your Jacobian, you really need a square matrix to invert. I mean, if you talk to the folks in the math department, you can do other things, but we're going to keep it simple, relatively speaking, and try to solve just square matrices or solve using square matrices. So now we're going to have any number of unknowns and any number of equations that we're going to use to check to see if our answers are correct. And those have to match, right? You have to have the same number of unknowns and the same number of equations. So now our x is no longer a variable, but a matrix of unknowns. And our f of x is no longer just one equation, but a matrix of equations. And when I mean matrix of equations, remember, we're going to evaluate those at specific points. So we will end up with numbers. And the process is exactly the same. We're trying to solve for the exact or almost exact solution so that our f of x equations all come out valid, which means they're all set equal to 0, and that's the result that they come up with. And we're going to update delta x using that sequential linearization approach that we talked about last class that we met. And then we're going to update our value based on getting closer and closer. So you can see our delta x is the true value minus what the value should be. Go ahead and get that there. So now we have to expand our equations a little bit. And now we have to introduce the concept of partial derivatives. And I know for the ECE students who take, was it 252 or 253 or 258 or 259, there's so many numbers. It's linear algebra and differential equations. Actually, no, it would be Calc 3, I think, is when you do partial derivatives, typically. But for EET students, we don't take vector calculus. And so we have to spend a little bit of time understanding how to do partial derivatives. And partial derivatives really aren't that difficult. The way that I like to say how to solve partial derivatives is you assume that the variable in your equation that you're not taking the partial with respect to is a constant. So it's a number. X1 is no longer X1, it's 7, it's 2. It's a constant number because you're not allowing that value to change. You're not like taking the differential of a variable that it's not changing. So you can simplify it down quite a bit. So you've got all these partial derivatives in here, and you just take partial derivatives for however many variables you have and how many equations. That's where you end up with a square matrix. So number of variables is usually going to be equal to the number of columns, and the number of rows is going to be indicative of the number of f of x equations. So these are broken out in terms of taking partial derivatives of every variable based on each of the functions, and we go all the way down to our n functions. So now we just put it in matrix form because it cleans it up nicely, doesn't it? Our f of x true is equal to the f that you evaluate at that x that you either specified or you've come up with by using this Newton-Raphson iteration. Here's your partial derivative matrix. We're going to call that the Jacobian. And the nice thing about partial derivatives is if you have any background in it at all, it helps you determine sensitivity. So if you're in power systems and you want to figure out how much a change to one parameter will make to the system, you can look at this Jacobian matrix and you can say, well, how sensitive is a power at bus 2, the real power at bus 2, to a change in angle at bus 72? You can actually see that in this matrix. So that's our Jacobian, and then our delta x's, again, those are the ones that we update, and we're going to neglect all those higher order terms. So just formalizing again, that's our Jacobian, and we're not going to write down all the variables because there's essentially an infinite number of f of x or partials that you have to do. Again, just based on the number of equations and variables you're trying to solve for. All right, let's use our approach to solve the Newton-Raphson approach to solve these two nonlinear equations that you can't just plug in. You can always plug and chug, but you can't come up with any substitution process. It's not going to work for you. So the first thing we need to do is I've solved for it, but let's go ahead and write what our Jacobian is. So normally what I do is when I specify my Jacobian, I kind of give you positions. So this will be my variables. We'll define the columns, and the rows are each of the functions I'm trying to solve for. So once you specify that, then you can see, well, I need the partial of x1 with respect to x1. You just grab the row and the column, and then you know which partials you need to take. Because surprisingly enough, figuring out the partial derivatives you have to take is actually a little bit of a process. It's not the easiest thing. Then we do the partial of f2 with respect to x1 and the partial of f2 with respect to x2. Now, it's important for you to go ahead and lay out your Jacobian in a consistent manner, because when you set up your rows, your equations that you're plugging into your matrices, as well as your variables that you're solving for, you're going to lay them out in a very specific pattern, and they have to be so that it makes it easier to solve for, particularly when you're looking at your sensitivity matrix. So we're doing rows, F1, F2, all the way to the end, and then columns, the variables, what we'll go through. We'll actually define what those rows and columns need to be once we actually start writing power balance equations. So I've got to take 4 partial derivatives. I need the partial of f1 with respect to x1. So that's going to be the partial of 2x1 squared plus x2 squared minus 8. And I'm taking the partial of that with respect to x1. So x1 is the only variable that is allowed to change. All the other ones are constant. So if you can get, it's easier to, you can substitute in and change these variable names as much as you want. I'm pretty comfortable doing this, so I just leave it as is. But I see the partial of 2x1 squared is 4x1. The partial of x2 squared with respect to 1 is 0, right? There's no x1, so no matter how much I change x1, x2 squared doesn't change, does it? I can go from x1 to minus infinity to plus infinity, and x2 squared does not care at all. So that's why it's a 0. It doesn't change in any way, shape, or form. And then finally, minus 8 is a constant as well, so that becomes 0. So that's my first partial. My second partial, and you can do these in any order you want. I'll just do the rows, and then I'll do the columns. So that's the partial of f1 with respect to x2. That's equal to 2x1 squared plus x2 squared minus 8 with respect to x2. So again, 2x1 squared can be, if you change x2 all day long, it has no impact on 2x1 squared. So that is 0. x2 squared, that is sensitive to changes in x2. So that becomes 2x2. And again, minus 8 is constant, doesn't matter. It stays the same. Now we'll do the partial of f2 with respect to x1. Sorry, this is acting a little slow. And that's with respect to x1. Hopefully what you all can see, 2x1 is the first one because x1 is allowed to change. x1, x2 is just going to be x2, right? Again, x2 is a constant when I'm taking the partial of that with respect to x1. So there is no change with x2. So I just take the partial of x1. I can factor it out even as treat it as a constant. And then this is, whoop, not sure why that zoomed in. That's plus 0 and plus 0. And the last partial I have to take is with respect to x2. And that becomes x1 squared plus x1, x2. I'm not sure why this is happening so slow. Minus x2 squared minus 4 with respect to x2. That's equal to 0 plus x1 minus 2 x2 plus 0. So now that goes into my 1, 1 position. Goes into x2. This is position 2, 1 and 2, 2. All right, those are my partials. Anybody have any question on how to do partial derivatives? Again, it's not hard if you just remember or recall that the variables that you're not taking the partial with respect to are treated as constants. Then it's just like taking the derivative of 2x squared. The 2 is a constant. That's the same thing as x2 times x1 squared. The x2 is a constant. It doesn't change. Okay. All right. So that's our delta x1, delta x2. We've got them set to the Jacobian, raised to the -1. And then we're going to evaluate at f1 of x and f2 of x. So we have two values of x we have to substitute in. We take those same values for x1 and x2 and substitute it into our Jacobian. And then we update our delta x values, which means we update our x1 and x2 variables. And then we rinse and repeat until the error of the largest one is less than some preset value. So let's take a look. We'll guess 1 and 1. Just a guess, right? Logical guess, hopefully, but a guess nonetheless. So on our first iteration, so going through and processing, we have our x value of the previous iteration. So that's x0. So 1, 1 minus the Jacobian. And then that's 1 over the Jacobian. So inverted. Evaluated at x1 equal 1 and x2 equal 1. Then we plug in our value of f of x. So we have 1 and 1. And clearly our numbers are not right because these are supposed to be 0. That's not anywhere close to 0. That's -5 and -3. So we're a long way from our answer. So we run through our process and we end up with our next iteration results, 2.1 and 1.3. Now we plug those into our f of x equations and we can see that 2.51 and 1.45 are not 0, but they're a lot closer to 0 than -5 and -3, right? Both of those have gotten quite a bit closer. So we run through our process again and update, and now we're at 0.1284 and 1.212. We plug those into our f of x, and we end up here. So are we at 0? No, but we're far closer than the previous iteration result, right? We went from 2.51 to 0.155 and 1.45 to 0.09, essentially. So much, much closer to 0 than before. So we feel like these results are going to converge to a valid solution. Diverging means they're getting further and further away from 0. These appear to be getting closer and closer to 0. So at this point, if you're satisfied with an error of less than 0.2, you're done. Stop. If not, continue until you get to the point where your error is satisfactory. I did this code in MATLAB. And And you can see again, I got the clear and the CLC at the top. I've got my initial guesses. And so this one is a little bit different. So this one you might need a little bit more of an understanding of MATLAB. It's not necessarily complicated, but it is more complicated than just, spelling it out. So what I've done is I put everything in a matrix. I have an X matrix, an F matrix, and a J matrix. You could keep them as individual variables. You could call it X1 and X2, but it can be a little more housekeeping when you're trying to set up in a matrix. So I just set it up in a matrix initially, and my X matrix is a column vector, which means it has one column and 2 rows. And I've set that up to be 1 and 1. So essentially what the outcome of this right here is, I guess it doesn't want to, when these two are processed, you're going to end up with a matrix that looks like that. Okay. My F matrix also is going to have, it's going to be a column vector. And my Jacobian, when it all is said and done, it's going to be a square matrix, a 2x2 matrix, which is what I need because remember, my X, which is a 2x1, is going to be equal to a 2x2. When I invert the Jacobian, which is a square matrix, I still get a 2x2. And then when I multiply that, this is a 2x1, and then I have to add to that a 2x1. So dimensionally, you end up with a 2x1 matrix. So I set up my X matrix. I set up a delta X equal to 0 just to go ahead and kick it off, but I don't actually need to do that. I probably could just comment that delta X out and continue to process it there. And then my N value is, I set it equal to 0. So this one, I gave you a little bit of a different approach to set up the matrix, actually to set up the while loop. In this one, I actually said if the maximum of the absolute value of dx, so my maximum error, if it's greater than 1 times 10 to the minus 10th, or if I'm on my first iteration, I want to force it through my first iteration, okay? So if you're pretty confident, which most of the time you will be confident that you don't get the right initial guesses, I'm going to force it to go through and run through one result. Because inside my while matrix, I'm calculating my F1 and F2 to see if those are 0. And then I'm going to go my Jacobian, my delta X, and then I rinse and repeat. So now I'm not looking to see if my F of X is equal to 0. I'm looking at my delta X. Is that okay? The ultimate answer is F of X has to be equal to 0, darn close to 0. But isn't the same thing as saying delta X is essentially, there's no change in X, right? So if there's no change in X, I probably should be done with my iteration because I'm not going to get that much of an improvement. So I'm giving you an option. You don't have to take this, but this is an option. If you would prefer, you can take a look at your delta X. If your delta X ain't changing, this isn't working for you. Meaning if your delta X isn't changing and you don't get F of X equal to 0, then it's not working. If your F of 0 if F of X is 0, then you're probably okay. So I just said, I'm going to take a look at delta X. If it's pretty small, I should be pretty close to my final answer. So I use either of those conditions to start my while loop or keep checking my while loop. And remember, don't get greater than 10 iterations, because if I make a mistake in entering in my formulas here, MATLAB is just going to iterate forever and ever and ever, and you're going to have to hit Control-C to stop it. So I stop it after 10 iterations. If it's gone through 10 iterations and it's still processing, then forget it. I'm done. So I calculate F1 and then F2. Again, put those in the column vector. My Jacobian, just plugging in my Jacobian and evaluating at those terms. I calculate my delta X, and in MATLAB, you can do all kinds of things to invert a matrix. This is called left divide, so that's another way of doing taking the 1 over and then multiplying. Just call it left divide. And then I update my x1, x2, I update my iteration counter, or I increment it by 1, and then I rinse and repeat until I get that going. So let's bring up the actual MATLAB window. Let's try to scooch that over here. And we'll just walk through each iteration and see how that compares to what we had. Yes, sir?
Your left divide, so we say J over F, right?
J left divide over X. Or it's not over X, it's J left divide by X.
But supposed to be the J supposed to be the J power minus 1. So
That's what the left divide does. It inverts it. It inverts it and multiplies.
what J? Be the left divide. F divided by J.
No, if you do the left divide, it's X divided by J. That's what the left divide does. The right divide is just a standard,
Division.
right? That's standard division. Yes.
Oh, even use the better slash.
That's the left divide. Yeah, it's the opposite direction, right? So again, that's a quirk of MATLAB. You can also use invert and multiply, but it just saves a little bit of processing time. All right. Let us run it. And I will run each line so you can take a look. So F, exactly what we said in the slides, right? -5 and -3. Now I'm going to run through my Jacobian, and I'm only plotting it at the end. My Jacobian, 4, 2, 3, -1. Let's check and see if that's what we have. 4, 2, 3, and -1, right? So those check out okay. Oops. Let's keep going. My delta X is 1.1 and 0.3. Now I'm going to plug that in for my X. I get 2.1 and 1.3. Is that what we had here? 2.1 and 1.3. So my first iteration matches what we calculated in MATLAB. Now I'm going to go ahead and do the next iteration. 2.5 and 1.45. And I'm going to just put up all the J and the X on one screen so you can see. So now my F is 2.51 and 1.45. 2.51, 1.45. My Jacobian, 8.4, 2.6, 5.5, and -5. Let's see how close that matches up. Looks exact. And then my X is 1.83 and 1.1212. 1.83 and 1.212. Now I'm going to go ahead, because the last thing I have on my slide is my F value. So next iteration, 0.1553 and 0.09, which is what we have. So let's keep going. That error was acceptable on the slides because you didn't want to put 10,000 iterations there. But let's go ahead and see how long it takes to get to 1 times 10 to the minus 10 for an error. So this is the third iteration. Is it going to run through again? Yep, it's running through again. And look at my delta X. Now I'm down into the 10 to the minus 4. But I want it to be less than 10 to the minus 10 or 1 to the minus 10. So it's going to keep running. Now I'm at -8. So my delta X is still not there. So it's going to run through one more iteration at least. But my X values are hardly changing. If I look from the previous 1.891, 1.2060, at least displaying to 4 digits in MATLAB, you can't see the difference. And that's because the error is so darn small. But I said I want to stop at -10. So delta X is so small, it indicates as 0. Can't even display it on the screen. So let's see if it's done. Yes, it highlights the end. So it kicks me out and then it stops processing. So it took 5 iterations, right? Actually 6 if you count the 0 iteration. So it took 6 iterations to get to an error of less than 1 times 10 to the minus 10. And you can see my F values, and I can even type those here in MATLAB. My F values are 0. If you want to be more accurate in MATLAB, and I don't know if people, probably you all have seen this, but if you look at your variables, you can display your variable and you can display them as long decimal. And let's see F again. Whoops. It's not displaying it. You know, I'll just try putting F over here. Does that do it? No. Should be displaying it with more precision. Yeah, this is even showing that it's 0. So even with the long decimal, you can't even see it deviating from 0. My X value. So let's click on X. And we'll change this to, so that's what your X value, all the way up, all those numbers. Now, clearly, I wouldn't expect you or anybody to do this to get that level of precision because it's only so accurate based on the input data, but those are your final answers. 1.809, blah, 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 and 1.206, blah, 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 blah. Okay? And even with solving these two equations, it's very difficult to visualize where they're going to intersect, right? Because you would have to have, you would be plotting X and X1 and X2, and you have F1 and F2, and you'd have to plot where they converge. So you can do it on 2 dimensions, but you can only really do 2 equations and 2 unknowns before it's very difficult to visualize. You could maybe do a 3x3, but then you'd actually have to start being able to physically rotate things to see in 3 dimensions. So it's just not practical, whoops, to do beyond that. Okay? Question on that? Make sense? Don't make sense? If you start, let's see if we start at 0 and 1. So let's clear all of those. And let's change this to 0 and 1, and we'll run it and see what happens. So it still got there from here, right? It still got to pretty much the same answers, but you'll notice it took 9 iterations. Okay. So if you go 1.8 and 1.2, and you run it, it only took 4 iterations. So the closer you are, your guess, your initial guess, the closer you are to a valid solution, the more efficient this process is. Now, for us, doing simple one like that is no big deal. It doesn't take hardly any time to do it. But again, if you got to do 1 million equations and 1 million unknowns, this can take weeks of processing time. So you want to be fairly close to where your guesses are, because if you spent weeks and you put in some wrong data, then you got to wait weeks again to do it. It makes it really more difficult. Yes, sir. No. 1-1 is not always best initial guess. The best initial guess is dependent upon the system that you're examining and your expertise as to what would be a typical solution that I would have. I kind of knew, like, closely that the numbers would be 1 and 2 or 2 and 1. So I just said, well, let's just pick 1 and 1. You can pick anything you want. If we go to 0, 0, though, I think it crashes. Let me try it. See, not a number. So sometimes if you just specify both equal to 0, you can't process anything because your Jacobian is going to be, most of the time, you're going to try to invert a matrix of zeros and it's not going to work. So that's why I said, you know what? Let's go ahead and not get that close to the final answer. We picked 1 and 1, and then we got 6 iterations, not too painful to get there. Okay. Questions on how to do that, because that's what you'll be doing in lab. You'll be doing partial derivatives with sines and cosines. And just because you take a partial derivative doesn't mean it doesn't mean you have to get rid of variables. Like if you take the partial derivative of x1 with respect to x1, you get 1. But if I take the partial derivative of cosine of x1, right, I get the negative sine of x1, right? So it just becomes the x1s don't have to disappear. It's perfectly fine. They don't have to go away. It would still go ahead and evaluate out. Okay. I have another one I can show you. I thought I had it up, but I guess I didn't. Oh, I did have it up. So here's another one. So you can see, and let me put that on whiteboard. Where's whiteboard? Here it is. So I have f1 is equal to x1 squared plus x2 squared minus 4. And then the next one is x1 squared minus x2 plus 1. So x1 squared plus x2 squared minus 4, x1 squared minus x2 plus 1. So I'll give you 5 minutes. So I'll give you 5 minutes. Do the equations that you can go ahead and solve Newton-Raphson.
Finding the podium.
Find the whole thing. Show me how you'd set it up. I'll pause the video because nobody wants to be paused or watching dead time. So I'll pause the recording and restart once we get back on. So 5 minutes. Okay. For those of you who are making good progress, feel free to keep working ahead of me. I will sort of show you how I would tackle this problem. And yeah, you can either watch on video or you can keep proceeding forward. But essentially what we're trying to do is we're going to check our f of x, right? And I don't even remember what I told you to guess. 1 and 1. So check f of x at x1 equal to 1 and x2 equal to 1. So the first thing we'll do is plug in 1 plus 1 minus 4 equals negative 2. f2 of 1 comma 1 is equal to 1 minus 1 plus 1 equal to 1. So maybe that's the best thing to do, which is check to see if your f of x equations evaluate to 0. Because if you are, you don't even have to do Newton-Raphson. You're done. If these had been the correct answer, stop, no more work. You don't have to do that. But they're not, so we've got to go ahead and update every time. So we have to solve for delta x, which is equal to my Jacobian raised to the negative 1 of x times f of x. And then our x value is x, I'll call it previous, plus my delta x. So only thing I'm missing is my Jacobian. So let's zoom out a little bit. So my Jacobian, and if you remember what I said, was go ahead and identify the rows in the column, f1, f2, x1, x2, partial of f1 with respect to x1, partial of f1 with respect to x2, partial of f2 with respect to x1, partial of f2 with respect to x2. How many of you all actually identified which Jacobians you needed to determine? You'll be good, because that's the thing, right? Is you need to know, I mean, it's kind of obvious here, but you'll find when we start writing our own equations, it's not so obvious. But it's good to show which partials you have to take. but then also where they're going to be located in your Jacobian. So the first one I'm going to do, just the first one that's in order, the partial of f1 with respect to x1 is 2x1. The partial of f1 with respect to x2 is 2x2. The partial of f2 with respect to x1 is 2x1. And the partial of f2 with respect to x2 is -1. So my Jacobian is going to be equal to 2x1, 2x2, 2x1, and -1. So at this point, I'm ready to solve for my delta x, which is equal to 2x1, 2x2, 2x1, -1, raised to that power. And then I multiply it by my f1 of x, x1 squared plus x2 squared minus 4, and my f2x. Those are my delta x equations that I'm solving. And then to solve for x, 1 and x2, and I'll just put them in a matrix, it's x1 and x2 previous plus my delta x. Let's see if I've got that done in MATLAB. So here are my, and I use the same thing for examples. Here's F1, F2. There's my Jacobian. You can check and see if that matches what I have. Just be careful, because if you look right here, that first element that you define for your row, that's important, right? Because we're using x and delta x and Jacobian. Those are matrices. So now we have to index correctly. So be very careful that you've got those indexed properly. It's really easy to make a mistake in MATLAB because the numbers start to, jostle together. And again, that's why we have that iteration count. So then I have my delta x and my Jacobian. I have my delta x, and then I update each time. X1, X2, and then rinse and repeat. Hello, can you hear me?
Yeah, I can hear you now.
Zoom just shut down and restarted. I don't know.
The last thing I heard was rinse and repeat.
I swear I'm not doing anything weird. I don't know why it's dying like this, so I apologize. Maybe it's my computer. Usually the Wi-Fi is pretty reliable, so I'm surprised it's quitting, but you can hear me still?
Yeah, I can hear you.
Yeah. So what I was saying is at the beginning of the semester, I told you about a very useful tool Do you remember what I said? It's called MATLAB. Why would it be useful? Not required in this class, but can you see why doing MATLABs and using while loops? I can do 4 iterations in, you know, how long it takes to write the program? 5 minutes. If you had to do that in your calculator, how long would it take you to come up with a valid solution? 30 minutes? 20 minutes? So this is the reason why I encouraged you so much. And you don't have to use MATLAB on the test. You can certainly do it with your calculator, but I only want to see 1 iteration result. If you do MATLAB, you know, you just run the while loop, right? It's pretty simple to do it. So this is the primary reason. I mean, I love MATLAB for other reasons, but for you all, is it worth it to learn how to do it? I don't know. I mean, you can crank these out pretty quickly. And when we start to do power balance equations, your equations get a lot longer. I'll give you a sneak peek. Let's see. So this is a 3-bus example that we'll be doing in class. Those are the equations. You have to do, each time you have to solve 12 equations for numbers, then you have to invert to get your 13th equation, and then you have to add and rinse and repeat. So you have 10, 11 equations to do maybe 5 times. So you have to run through 50 different or so calculations to end up with something. So not saying you have to do it, but hopefully you're starting to see the value of like, yeah, maybe if I write these equations and let MATLAB just auto update all the variables, MATLAB will do it for you. And then you just keep doing it over and over and over and over and over again. Very, very simple. I'm not expecting anybody here to be a computer programmer. This is just basic while loops, right? Like anything in here, there's a lot of equation stuff, but it's just multiply, divide, add, subtract. The only thing that I would say takes some coding expertise is that, right? Setting up a while loop. And I think ECEs, EETs, I know there's some bio, chemies. I think all engineering disciplines are required to take at least 1 programming class, right?
I know some, but they don't have that condition
But yeah, that's what I'm saying. There's a bunch of different ways to do this. So I did this one a slightly different way on this one. So we'll talk about that when we get to it, but there are multiple ways that you can set it up. So I'm just showing you different ways. You can decide which one you want to implement. They all will be perfectly acceptable. But I guess what I'm saying, for those of you who are in engineering, you should have had a programming class that you should know how to do whiles and if-thens, right? I mean, that's not an unreasonable expectation. And I'm not even expecting you to do it. I'm just saying, if I ask you to do a while loop, it shouldn't be like, what's a while loop? I've never heard of that, right? I mean, most of you all would have been exposed to that, and it's pretty simple syntax. So anyway, without getting too much sidetracked, I just wanted to talk a little bit about that. So now we're going to go ahead and start to apply these, and we're going to have to set up our equation. So we got to build Y-bus because we need to figure out how to calculate currents from voltages. So you're going to build Y-bus, you're going to build your admittance matrix, and you're going to invert your Y-bus to get your Z-bus, which is not as useful in some cases, but in some cases it is. But we're actually going to use our Z-bus. So if we wanted to solve a problem for calculating power, we've got 2 buses. So we have a voltage at each bus. Then we have a Y-bus. So if we invert our Y-bus, so this here is V, Y. That's our I matrix. Then we can calculate from here the power injected just by using our combined approach using Y-bus. We have an S1 and an S2 there. So we're going to actually take that into account. Actually, let's do one more. We also can do it with current and back calculate voltages. So we can get, any values we want, right? So we can see here, we get voltages. Over here, if we have a way of calculating currents, we can get voltages there. So either one will work to calculate power flows. So now we're going to take advantage of that, and we're going to go ahead and apply all the techniques that we have to figure out how to solve these nonlinear equations. But we have to figure out how to write these nonlinear equations that we're going to solve for. So we don't know the bus voltages, right? We can predict them, but we don't know what they are. We might know what a few of them are. We can monitor them, but the most part, we actually don't know what the magnitude and the angles are
According to B, the class has been canceled, so that's it, guys.
Thank you.
Alrighty.
Rita.
Not a problem.
Yeah, Paul said that we're good here. I'm in class right now. I just joined in my phone. He said we're just gonna pick up where we left off next class.
Okay, good. Thanks for confirming.
Yeah, I just sent it in chat too. So you guys are good to go, and he'll
Right.
probably send out an
Thank
email
you.
or whatever.
Sweet freedom.
It's not a lot of that, like, probably it's only, you know, like a lot of that stuff in the front end, might have. That's all.